Okay, let's dive into this. Every single day, the world generates over 300 million terabytes of data. But we rarely stop to think about how it's actually packed away under the hood. So, welcome to today's Explainer, where we're going to embark on a pretty fascinating journey into the unseen infrastructure that powers, well, virtually all of our modern applications. Today, we're tracing the massive, multi decade evolution of data file formats. We're going to start all the way back in the 1970s and bring it right up to today's huge AI boom. It's really a story of constant innovation where every solution eventually creates a brand new bottleneck. Here's our roadmap for this explainer. First up, what exactly is a file format? Then we'll look at the row-based eras, followed by the columnar revolution. After that, we'll hit the AI data bottleneck. And finally, we'll wrap up with next-gen file formats. All right, section 1. What is a file format? At its absolute core, a file format is just a standardized set of rules. It basically tells a computer exactly how to encode, structure, and compress data so it can actually be stored on a disk and, most importantly, correctly interpreted later on. Think of it kind of like a language. Without a defined format, a file is literally just a meaningless, endless stream of ones and zeros sitting on a hard drive. These rules are absolutely foundational to everything in computer science, mostly because they completely determine how efficiently we can retrieve our information. Looking at our timeline here, you can see file formats have evolved dramatically across 4 distinct eras. Back in the 1970s, plain text was everything. Then, by the 2000s, huge data demands pushed us into binary rows. The 2010s? Well, that required a total paradigm shift over to columnar formats. And finally, today, we're right in the thick of the AI and multimodal era. What's really incredible about this timeline is how each era directly solved a major hardware or data scale bottleneck from the previous generation, only to, you guessed it, eventually run into a brand new ceiling. Moving right along to section 2, the row-based eras. So from the 1970s all the way through the 2000s, plain text absolutely ruled. We're talking about formats you probably use every single day, right? CSV, TXT, JSON, XML. In these formats, data is stored row by row in plain text. Now, the great thing about them is they're universal, they're human readable, and they are incredibly simple to generate or edit. But here's our first major bottleneck. They are extremely inefficient for large data sets. I mean, imagine trying to find a friend's phone number, but being forced to read the entire phone book from A to Z, including all the addresses and middle names, just to find that one number. It's wildly inefficient. To solve all that massive bloat, the 2000s brought us binary row-based formats. Think Apache Avro and protocol buffers or protobuf. Instead of bulky plain text, data gets converted into these super compact, binary encoded rows that are paired with an explicit schema. And this was fantastic for the era of event streaming. Systems like Apache Kafka absolutely loved this because data arrives one record at a time, making it super fast to write and heavily compressed. But of course, there was a catch. While it completely solved the storage efficiency problem, data was still organized by rows. So analytical queries trying to scan specific columns were still hitting a major bottleneck. That brings us to section 3, the columnar revolution. And this brilliantly illustrates the massive difference in approach here. Over on the row-based side, formats act kind of like a vacuum, sucking up billions of completely irrelevant data points just to analyze 2 specific columns. When big data really took off, this just became physically unsustainable. The bottleneck literally forced a change. But on the flip side, the columnar approach acts more like a laser. Famously championed by Apache Parquet and Apache ORC, this approach groups data by column instead of by row. So if you only want to know a user's age, you can completely skip all the noise and only read the age column. Let's break down exactly how Apache Parquet achieved this magic, because it really relies on 3 key innovations. Step 1 is the columnar layout itself, like we just talked about. If you query a specific field, the engine just completely skips all the other columns. This brilliant little maneuver is called column pruning. Step 2 is built-in metadata. Parquet files actually store minimum and maximum statistics for chunks of data right there in a footer. So if your querying is looking for, say, an age greater than 50, the engine can glance at the metadata, see a block's max age is only 40, and completely skip that entire block without reading a single row. Pretty cool, right? That's known as predicate pushdown. And finally, step 3 is advanced encoding. Since a column only contains one type of data, like only numbers or only dates, you can use really aggressive compression techniques, like dictionary encoding and run-length encoding. The impact of these 3 innovations was honestly nothing short of staggering. Parquet became the absolute gold standard because it slashed storage costs by, get this, 70 to 90%, and it accelerated analytical queries by orders of magnitude. Honestly, this single file format essentially revolutionized the architecture of modern data lakes, serving as the backbone for massive platforms we use all the time, like AWS S3, Apache Spark, Snowflake, and DuckDB. All right, moving into section 4, the AI data bottleneck. So modern workloads, specifically the ones driven by large language models, vector search, and heavy GPU computing, have actually exposed Parquet's limitations, and it's created an entirely new bottleneck for us. First off, Parquet has really poor random access. It was beautifully built for huge batch scans, but when an AI model needs to instantly retrieve just a single user's profile, reading the whole group is a massive speed bump. Second, we're dealing with high-dimensional data today. Vector embeddings can have thousands of floating point numbers per cell, and these super wide feature tables drastically slow down Parquet's metadata parsing. And finally, we have hardware bottlenecks. Older formats like Parquet rely heavily on CPU decoding, rather than really taking advantage of the immense parallel processing power of modern GPUs. Which brings us to our final section, Section 5, Next-Gen File Formats. Now, what's really interesting about this slide is just how staggering the performance leap actually is. The Lance file format specifically targets AI, machine learning, and multimodal datasets, so text, images, video, the whole shebang. By completely rethinking the columnar structure, Lance delivers up to 100 to 1,000 times faster random access than Parquet. It pulls this off because it natively supports advanced memory search algorithms like IVFPQ and HNS built right into the file itself. This lets AI find similarities almost instantly. It even lets you add or drop columns seamlessly through zero-copy schema evolution. Basically, it's engineered from the ground up for AI training. But Lance isn't the only player changing the game right now. We also have Nimble, which was actually developed at Meta, and Vortex. These formats are targeting extreme-scale machine learning feature tables and real-time query engines. They actually replace all that heavy metadata with zero-copy layouts like flat buffers. That essentially means data is read exactly as it sits in memory, without needing to be translated or unpacked first. On top of that, they utilize SIMD instructions, which basically let processors perform multiple calculations at the exact same time, along with GPU-friendly encodings. By shifting all that work away from standard sequential processing, they drastically cut down the CPU overhead that usually bottlenecks data loading in massive AI workloads. If you take away just one thing from this explainer today, please let it be this cheat sheet. It really ties our whole journey together beautifully. If your storage style is text and row-based, like CSV or JSON, your best use case is definitely ad hoc inspection, mostly because its primary advantage is just being human-readable. Now, if you need binary and row-based storage, you're going to use Avro for streaming pipelines thanks to its incredibly fast row writes. Moving over to binary and columnar, Parquet is absolutely your champion for traditional analytical queries, thanks to its high compression and super fast column scans. But for modern ML training and vector search, you really need an AI-native binary columnar format like Lance, because its primary advantage is just blazing fast random access. Which brings us to our final thought. The format you choose literally dictates the limits of what you can build. So as you sit down to architect your next application, you have to ask yourself, are you building tomorrow's AI on yesterday's bottlenecks? Understanding this kind of invisible history is really the first step to truly unlocking the future of data. Thank you so much for joining me on this explainer, and I really hope this helps you structure your systems brilliantly moving forward.